All right, thanks. Thanks for having me. So the plan is to talk about Clockwork. For those of you who don't know, the original Clockwork mechanism is essentially a toy field theory that came out about a year and a half ago. And it consists of n axions. So each of these axions has a U1 shift symmetry. And you arrange sort of symmetry breaking interactions between the axions such that only one U1 symmetry remains. And this remaining U1 shift symmetry protects sort of a light mode, which is a linear combination of the original n axions. And because of this peculiar sort of symmetry breaking pattern that it has, the weights in this sort of linear combination of the n axions are very uneven. They sort of form a geometric sequence. And as a result, this light mode can have very, very suppressed couplings relative to the couplings you wrote in your original Lagrangian for the n axions. And that's the basic idea. So if nothing else, I'll hopefully sort of go through that in detail and then sort of touch on a few sort of generalizations that sort of appeared in the literature. So sort of generalizing to other fields, transforming under other symmetries, and even sort of finding some sort of continuum limits. So finding extra dimensional models which deconstruct to something which looks like this clockwork mechanism. And if that doesn't take us to time, I will try and tell you about some new stuff that I'm working on with Nathaniel Craig, which is about getting clockwork-like properties, so sort of exponential suppression of couplings, but not with a Lagrangian with very sort of particularly with a very particular pattern of coefficients to affect some symmetry breaking, but just with random coefficients in a manner sort of analogous to Anderson localization on a sort of a 1D lattice. Okay, and that's quite interesting, but maybe we won't get there. All right, and please do interrupt. Okay. All right, so let's start off first not with n axions, but just with n complex scalars. These phi I, obviously each one has its own rephasing symmetry. And then we arrange these symmetry breaking interactions. All along this sort of ladder of phi I. So you can see that these break the individual rephasing symmetries. So if the guy on the right rotates by a certain amount, because of this exponent q, the guy on the left has to wind sort of q times as fast to keep up and keep the Lagrangian invariant. And this happens all the way along the lattice. So if phi n winds by a certain amount, then phi n minus 1 has to go q times as fast, then the next one q squared times as fast, ... Okay. So you can already see how we're getting this geometric sequence out. And okay, let's just say that all of these phis get Vev's modulus f. Okay? Sorry, I expand about the bottom of these Mexican hats, okay, in angular coordinates pi I. So these are these axion-like things. So here are the kinetic terms. Now each one of these has a U1 shift symmetry. And here, what comes out at quadratic order for the mass terms. So again, if this guy shifts a certain amount, this guy has to shift q times as much. And let's just assume that one of these pi I couples to QCD, or something that looks like QCD. So we'll call that index B. let's say, has characteristic decay constant f, modulo some factor of alpha s or whatever, like so. So, you think of this as a lattice, right? You think of this as a quiver theory. There's pi b here, coupling to gluons. Goes all the way to pi n. And because of these symmetry breaking interactions, you get down to one U1 shift symmetry. And let's say it has a generator T0. Okay. Now, up to some constant of proportionality, you can say, well, this contains a unit amount of the shift at the nth lattice site. And because of these interactions, then it needs to have q times the shift at the n minus 1th lattice site, ... Okay, so that's what the remaining symmetry group looks like. No, it's not at all important. Again, this is sort of the simplest toy model you can get, such that the coupling of the zero mode to these gluons will be exponentially suppressed. But no, it doesn't mess anything up. If you start dressing this quiver with more things, like, yeah. Okay. So yeah, what is this zero mode? Well, you can make the substitution pi I equals pi 0 over q to the I. And you can just sort of squint at this Lagrangian and see, if you make this substitution in here, because this x factor of q, all of the masses cancel, right? So this is sort of the correct zero mode, the correct normal mode, which will make all of these mass terms cancel. And you can see how its coefficients actually mirror the geometric sequence you have in the symmetry generators, because ultimately this shift symmetry is what protects the zero mode, and hence sort of gives it all its couplings. Sorry.
Yeah, I thought probably I just have some misunderstandings or something. I mean, for your first Lagrangian, you write there, suppose I put a charge 1 on the most righted one. And then
yes.
At my most left-handed one, I have already this q to the n power. This already sounds like you already, by setting those, explicitly making those setups, you already have a super big charge or super small charge, and then in the end you play with something and you claim that you get a exponentially small coupling or not. But maybe I understand it wrong, but it sounds like you just have get a super big.
So okay, no, not at all. So I'll come to that in a second. So it's more easily understood in terms of sort of a clockwork photon model, where it's a lot more clear what the actual charges, what the actual lattice of charges is. I mean, it is true in this model. You can redefine what your individual U1s are up to a certain extent, and then you can say that. Then it's sort of unclear what the original charges are of all of your sort of test particles.
But just to follow up on what you asked, so supposing I just wanted to, so what you got is an exponentially small charge.
Well, I disagree with that. I would say charges are integer. Well, I mean. We can always work in a normalization where charges are integer. Again, it's a little bit vague. It's a little bit vague when you're talking about scalars, but in the vector model, it should be perfectly transparent. But sorry, carry on. Hopefully, all will become clear. I agree. I'm playing fast and loose with the normalization of these fields. But yeah, we'll. That's probably best. Let's talk about the charge lattice when we get to the photon model. Yes.
I can also take all the x and all the lambdas to be different.
Yes.
And how do you get it?
So, I mean, if you just perturb them by like a small amount, it doesn't change. It doesn't change anything. You still get. I mean, regardless of what each of these say, fi's are, you will still get some factor q, which is approximately integer. Let's say it's just some number greater than 1, and you still get this mechanism of this one having to wind a lot faster than the next one. So regardless of exactly what these f's and these q's are, you will still get the sort of this exponential hierarchy of winding.
Vary them by a lot? No.
Well, okay, so you could put some bound on that. As long as the sizes of adjacent f's don't vary more than a factor of q between adjacent lattice sites, you will always get more winding going up the chain like so. So you always generate some kind of hierarchy. Yes.
Can I comment on that point? Because you look at some mechanism in our reduction mixing paper. And there we ask the question, suppose that we just take so you can think about the last term as something which has positive and negative masses, right? So here you choose all the masses to be negative and equal to each other, right?
Yes, correct.
But then assume that I'm just using a dice and I'm throwing it, and in some sides the mass will be positive, some sides the mass will be negative. Okay, without assuming the different thing is fine-tuning, because the masses of course are relatively diverse. So they could be, of course, the natural, we should expect all of them to be of the same order, but we don't control the sign. So then we ask the question, what are the implications of that? And the implications are like that. So suppose that I have like two sides with positive mass, where the symmetry is not broken yet. Okay? Then what you can think about is you can integrate the massive modes, and because you don't break the symmetry. And then you get a link between a side I and I plus 3.
Mm-hmm.
Okay, because you integrated the I plus 1 and I plus 2. Now, this coupling will be of the form phi I plus 3 to the power of 27. Okay, because you still need to, of course, the U1 is still conserved.
Mm-hmm.
Now, you get highly irrelevant operators. And then it's becoming a statistical question to ask what is the probability to have more than 2 or 3 sites with a positive mass and not negative mass. And the implication of that is now when you get this very high power of irrelevant operators, then you get another massless mode, because effectively when you have phi I to the power of I don't know what, then it's becoming highly suppressed contribution to the mass, so effectively you get another Goldstone. So you don't have only one relaxant, but now you have another Goldstone which goes down.
Okay.
And this amounts to basically some form of fine-tuning, but it's a very weak effect. It's logarithmic fine-tuning as a function of n. Of course, if you have many sites, the probability not to have another like Goldstone or relaxant is very small, but it's just a log effect.
Okay. So I don't know what I'm talking about in this regard, but presumably in that example, I mean, regardless of how relevant the operator, the symmetry breaking structure is still the same. You still get the same factor of q to the n by the time you get to the end.
For this mechanism to work, you need one zero mode. If you
Sure.
have a few zero modes, then you can study their potential and see it doesn't satisfy its requirements.
The other zero modes, but there'll still be one zero mode, which is presumably protected by this exact symmetry, presumably.
Yeah, okay. I'm just saying that
Sure.
the other one will be, its mass will be driven just by extremely irrelevant operator, therefore its mass will also be
Yeah. Yeah, so absolutely. Some of these coefficients will be small, and that affects the spectrum of the heavier modes. All right. Okay. So for completeness, let's just make this substitution and get out the Lagrangian of the zero mode. So this is the kinetic term. This is bounded above by some like order 1 geometric sum. Okay, so this is essentially an order 1 number, assuming like q is say 3, like some integer bigger than 1. What is not an order 1 number, however, is the suppression in the coupling to gluons, right? You get this q to b suppression. So again, if you couple it to the right-hand side of the lattice, this could be q to the n and very large. And the merits of this model.
Where to look at the interaction terms like pi to the 4, let's say, how would they scale q?
What? It is. Yeah, although this is an order 1 number. This is an order 1 number, so. No, I don't see how it's necessarily strongly coupled. I mean, so okay, this is an order 1 number, so the rescaling is not that big, and certainly in making this substitution, okay, modulo factors of n from summing over many sort of pi I, you get a suppression of q to the I for every 0 mode insertion of the 0 mode field that you get. So. I don't see how it's necessarily strongly coupled. Like each okay. Not to my knowledge. My naive guess would be clearly in making this substitution, every insertion gets suppressed by this amount. All right. Okay, so the merits of this theory are that, well, you get a very, very enhanced decay constant. So much so that if you, say, start off with some generic sub-Planckian f, you can end up with an effective decay constant for this 0 mode, which is sort of trans-Planckian. You can end up with a very flat potential, which may be of interest if you want to construct theories of inflation out of this. Note, however, that it doesn't suffer necessarily from some of the problems you might expect, because if you try and go to larger and larger field values, if you try and make larger and larger field excursions at a sub-Planckian scale, sort of at a scale given by sort of root epsilon f, all of these other modes come in and sort of UV complete your theory. So you realize what looked like some kind of trans-Planckian decay constant was just being mimicked by a load of like n axions sort of winding in a very, very, very particular manner. So it's a way of getting in the IR like a very, very suppressed trans-Planckian, even if you like, decay constant. That's the neat thing about this theory. Okay. So the photon model. So this is originally, I should write down references. It's originally written down by Prashant Saraswat. This is Choi and Im, and Kaplan and Rattazzi. Okay. Sorry.
Non-physics comment here, just about the reference. It has nothing to do with my work. But I think the original Clockwork paper was written 1 year before these two papers by Choi, Kim, and Yoon. And the title is Natural Inflation Multiple Sub-Planckian Axions. So
well, that sounds about right.
What's that?
That sounds like the title is very suggestive. Okay.
To get the credit, not these two papers.
Okay.
Because Choi and Im are common, and that's the 1 year before these two papers.
Okay. Noted. All right, so the equivalent photon model. So we have n photons, n field strengths in the kinetic term, each with this gauge coupling G. So we're working this normalization when the gauge coupling is outside the kinetic term, specifically for these reasons about the symmetry group and the charges. In this normalization, the gauge transformation of the A's is just a d alpha with no sort of coupling in front of it. A d alpha where alpha is between 0 and 2 pi. So the reason for this, it should be an obvious probe of what's going on in the symmetry group and charges, etc., etc. And then we have a series of mass terms, which you can imagine as coming as from vevs of some scalar field, with unit charge under one and charge q under the next one, which again generate a symmetry group with sort of a geometric sequence of weights amongst the original generators. And let's say we just couple some test mass to the site at the end. Now, we can make the same substitution. So, like so. But note, if we worked in this normalization, we would get a non-integer charge here for the test mass under the 0 mode. Just sort of making a substitution, you get a 1 over q to the n. Right? So very deliberately, I'll work in the normalization where if all of the test particles have integer charge, they'll have integer charge under the 0 mode. Okay? And this is exactly the normalization such that if A0 shifts by 2 pi, or sort of a d alpha running between 0 and 2 pi, all of the AI will shift by multiples of that, integer multiples of that. Okay. So this normalization is chosen specifically to keep A0 normalized to the symmetry algebra as we started off with the gauge coupling out here, if that makes sense. Okay, so we make this substitution. So as promised, this test particle has unit charge under A0. So what essentially happens is you get an extremely suppressed gauge coupling, and if you couple to the right end of the lattice, you sort of keep your unit charge. That's what's going on. So okay, what's the merit of? Thank you. Okay, so what's the merit of this theory? So analogous to sort of the trans-Planckian versus sub-Planckian thing that we had up here, we can think about the weak gravity conjecture in this theory. So it comes in multiple forms. Generally, that there should exist some particles whose charge is greater than their mass in some units in this theory. In particular, you can think about the so-called magnetic weak gravity conjecture. So that says this theory should have a cutoff at or below g times m Planck, sort of the coupling times m Planck. That is, some new physics should come in at or below that scale to do with quantum gravity. Now this theory may satisfy the weak gravity conjecture, or the magnetic weak gravity conjecture. But if you Higgs away like n-1 of these massless photons, you get this theory with a very, very suppressed gauge coupling. And this may not satisfy the weak gravity conjecture. This has a very, very small coupling. So that very, very small coupling times m Planck may not actually be the cutoff for this theory. There could be no new physics appearing at that scale. You would have to go sort of much, much higher. This is the magnetic weak gravity conjecture, as I believe it's called. Well, so it's relevant because it depends exactly on this gauge coupling. Sorry. It is that there should be new physics. Yeah, there's some effective cutoff of this theory, which is approximately at or below the gauge coupling times m Planck. Yeah, this is in a U1 gauge theory. And this is an example given in this paper of something which perfectly satisfies this conjecture. But sorry. Sorry.
So I even don't see, I'm blank in neural random or something. Why does this have something to do with
Well, so okay. In that, I am of course not an expert, but it is presumed that the interactions of all U1 gauge theories with some sort of complete theory of quantum gravity will satisfy this conjecture. Again, it's motivated by sort of consideration of decay of extremal black holes, so that carry some electric or magnetic charge.
Sorry, I don't understand. Claim that you can get around the weak gravity?
Well, no. So,
Say that the weak gravity conjecture is wrong? Or?
no, absolutely not. This is so. This is an example of a theory which may perfectly satisfy some or all forms of the weak gravity conjecture. However, if you do this Higgsing, in the IR, it looks like it violates it because of this suppression of the gauge coupling. So the
Neither this theory doesn't have the
Extrapolate to high energy, you have to indicate what the limit of the states.
yeah, absolutely. So
Lambda is sufficiently high, a large number of these params.
yeah, so I mean the point is you can make these VEVs very, very quite high, so sort of at the Planck scale, right? So you can have a complete desert between the Planck scale and down here, and if this is some sort of small coupling, then this will violate this form of the weak gravity conjecture. So it's an example of an EFT which in the IR appears to violate the weak gravity conjecture. Now the reason I'm telling you of all this is that it's sort of directly analogous to the sort of subplanckian, transplanckian couplings in the IR in the scalar theory. You can make this explicit as is done in this paper. By saying that you get all of your axions from the Wilson line of sorry.
Just saying that I'm not expert on it, but I remember that when they did all kinds of supporting, that it's an IR kind of black hole stuff, so they were saying that in the IR, gravity should be the weakest force. So it's not necessarily helps that in the UV you will correct. But again, I'm not expert. I just know that they give some supporting argument which related to black holes, not UV necessarily.
So the conclusion is that you are worried that this model also has a problem because you think.
Well, I'm not. No. I'm not saying this is a problem relative to gravity conjecture. This is just an example of a model. See this paper, which appears in the IR to violate the weak gravity conjecture, even though as you go up and it UV completes and all these modes come in, it is actually perfectly fine. again, the reason I'm bringing all of this up, is that you can construct each axion as some component of the gauge field, or a Wilson line rather, in the compactification of a U1 gauge group in an extra dimension. At which point this relation between apparent violation of the weak gravity conjecture and an effective sort of trans-Planckian decay constant relative to actual sort of sub-Planckian things can be made explicit. Because the decay constants of said axions coming from said compactification roughly go as 1 over the gauge coupling times some factor of the radius of compactification. So this is the sense in which all this nonsense about the weak gravity conjecture is analogous to what's going on there. I promised someone an answer about the sort of spectrum of charges, etc. Hopefully this is clear from what's going on. Okay. Sorry, it's important that the coupling runs. Oh, with respect to the weak gravity conjecture, that I simply don't know. I assume, as all of these constraints are sort of order 1 conjectures anyway, shouldn't matter too much, but I'm not sure. That's speculative. All right, you can also write down fermion models. Just say a few words about those. The symmetry breaking structure isn't quite the same. We're not taking one field and multiplying it by q times the other, but you can have a lattice consisting of alternating left and right-handed Weyl fermions, each with their own rephasing symmetry, and you can break that rephasing symmetry down using sort of some Dirac mass type couplings. And you get a very sort of similar pattern of Dirac masses out. So you can see an example in Giudice and McCullough, and an application of this in Hamby et al. To make a clockwork WIMP. So a WIMP with a very, very small coupling to the standard model, with sort of decay times on sort of cosmological scales, etc. All right. So there are a few questions about extending this. Sorry. I have probably missed some references, yes.
So for the fermions, there's something that's really confusing. I mean, we know that if we are having a loose diagram with fermions and deconstruct experimental, because the chiral nature of fermions, there is the fermion localization.
Correct.
It's exponential effect. And this is known at least from the Kaplan domain of fermions, and then there was paper on that in deconstruction, and people even use it before. Just because you exponentiate the translation operator, that you get the theorem of the exponential localization.
Yeah, specifically a flat.
Sorry. Just because it's sequestered, because you have many sites, and then you still have the theorem because of the translation operator of chiral fermions. So in that sense, I think here it's why not just call this sequestering or deconstruction? At least for the fermion case, we are familiar with that. And it's not, why is it clockwork? Just the name of fermion. You put a mass in the bulk and you get a fermion, which is exponentially, with a very complex exponential.
So I can't speak to why you should call it clockworking. I think the original motivation is just it has the sort of same pattern, the same pattern of couplings, essentially. You have sort of ones and Qs, and they build up to sort of a Q to the n suppression in the masses. I admit, so. Well, I mean that was pretty much the sum total. So you're absolutely right. So no, yeah. So it is true. There is no such thing as this sort of symmetry localization that we saw in the other two models, where you're breaking to some kind of non-diagonal symmetry group. That is not what is going on in these models, because you just have Dirac masses. You know, if one rotates, the other one has to rotate by the same amount to keep the Lagrangian invariant. So it is, in that sense, qualitatively different. However, in terms of the sort of quantitative numbers that come out, the sort of the QTN suppressions and things, and the mass matrices which come out, there are clear similarities. I think that's all I can confidently say about the Fermi model. All right, and that's all I'll say about the Fermi model. So, okay, there's the question of how you might want to extend these. So, for instance, if you might want to have a field transforming under a different symmetry group. And that is essentially a question of if you have some direct... so this is the question of if you have a G to the n symmetry group, what are the G subgroups that you can form out of it? Okay, this is something that I've worked on along with Nathaniel Craig and Isabel Garcia. All right, so the answer is, in short, that for most groups, you can essentially only form diagonal-like subgroups out of this G to the n. Okay, so a G subgroup which acts the same on all of the G to n subgroups in your lattice, and that that U1 along with a few other groups are special. I can give you a quick heuristic argument for that. So let G be a non-abelian Lie group. Let's give it generators. TAI. So this runs between 1 and n. This is some adjoint index. And give them canonical, some kind of generic Lie bracket. Okay. Note the Kronecker delta. So generators of shifts on different lattice sites trivially commute. Okay, and there's some structure constants here. Because it's non-abelian, at least one of these FABC is non-zero. Okay. Now let's assume that we have some weighted set of generators akin to what we had in the abelian case. So there's some weights AI multiplying the generators on each lattice site, Ti. Now, this has to satisfy the same commutation relations, the same Lie bracket. And if you substitute this line into here, use the bilinearity of the Lie bracket. Sorry?
Sorry, so for your AI there,
Yeah.
is that a common factor for any generators or for different generators, the AI can be different?
Oh, as in, you're thinking like so. So this is an arbitrary combination of any generators with sort of different adjoint indices. Is that what you're suggesting? Yes. So that's a bit more complicated than I wanted to get into. Again, see Appendix A of this for the full group theory result. Sort of Craig, Garcia, and Sutherland. But yeah, you can do this exercise, and you'll find some constraints on these matrices, sort of A, B. Sorry? So you can do the same exercise with this full matrix in. You'll find generically that this is constrained to be some kind of form of Lie algebra automorphism. So it doesn't actually have much effect compared to just like a delta there. But anyway, that's a bit more complicated than I want to get into. This is just the simple notion that you take a weighted set from each of the individual lattice sites. Okay. Well, oh yeah, it is very much assumed to have some I dependence.
Well, I think I have some examples where the AI can be different for different generations.
Yes, they will satisfy a very particular set of conditions. Again, as detailed in Appendix A. So the full result, if you want, well, okay. All right, just in this heuristic example, okay, you get two AIs on one side versus one AI on the other. Because you have to satisfy this Lie bracket, and because at least one of the FABC has to be non-zero, this will imply AI squared equals AI for all I, which is another way of saying each AI is 0 or 1. So again, if you assume that the generators of subalgebra take this form, then essentially they will generate no shifts on some of the lattice sites, and on the lattice sites they do act on, they will all act on sort of equally. So you essentially have to break the diagonal subgroup in a non-abelian case. Again, this is sort of suggestive of the full result, which is an application of Gorsat's lemma. If you want to work it out, you Google Gorsat's lemma. Yeah, as with most group theory things, this is solved by some French mathematician in the 19th century. But yeah, see Appendix A for the executive summary.
What if you would allow G, what if you would just consider subgroup H of G to give you an unbroken zero?
Yeah, now that's, okay, we asked about that. That's going to version 2. I can't recall the exact details, but it is, of course, more general. Yeah, okay, so there are obviously, I mean, okay, so there are obviously some trivial examples where you can restrict each G in the N. You can restrict to some Hn, and H can be some abelian group. That's a trivial example. There are some more complicated ones which which won't appear in just doing this thing.
G is SUN cross SUN.
Absolutely. So if G. Absolutely. So if G is some direct product or even some semi-direct product, chances are you can sort of engineer it. However, the point is, if G, so in particular, if G is any classical Lie group, so your SUNs, your SONs, the things that you care about, you have to take a diagonal subgroup, essentially. Or, some break to some subset of the Gs and then take a diagonal subgroup. That's the group theoretic result. All right. Shall I just take maybe 5 more minutes to say what the consequences of this is? Yeah. What? Okay. So you can just quickly think about what will happen if you try and do the same sort of clockwork mechanism, except with a non-abelian, with a non-abelian symmetry group. So take some Yang-Mills theory. All right. Here's the same Lagrangian. Okay, assume you're taking the correct traces over the adjoint indices in these terms. Now, the thing that's different is, of course, there are cubic and quartic interactions hidden in these Fs. You can make the same substitutions. And you'll find a massless mode, but the cubic and quartic interactions of these A0 will not be equal, as is necessary for gauge invariance. Okay, so that is an example exercise you can do to convince yourself of this group theory result. Now, that's not to say that all is lost necessarily. This mode is still sort of massless at tree level, and it could well be that despite subsequent radiative corrections, which may happen, it's still sufficiently light for some phenomenological applications. So again, there's an example of that in which, Naira Fonseca is at this workshop somewhere. Have some scalar example of this. So a lattice of non-abelian, non-linear sigma models, where they essentially do this. They have the same clockwork symmetry breaking pattern, and they show that the resulting mass of the zero mode, which is not quite protected by symmetry, is still sufficiently light for some phenomenological applications. Okay, so that's one way of getting around what might be perceived as a no-go theorem. Another way. Sorry.
So I mean, very naively, I see. So basically, your breaking will only go to the diagonal path. So if my breaking, for instance, is by a valve which is triggered by 1111Q, just like, for instance, think about deconstruction. While deconstruction, all of those valves are 111111. So I replace them by 1111Q.
So changing the values of these V's, you're saying?
Yeah, so every of these breakings is triggered by a valve which is 1111Q, for instance. Suppose
yeah, well, so the
your G is SU 5 or SO 5.
So the values of the VEVs doesn't actually affect the structure of the zero mode, right? So these can be anything, and we still need to make the same substitution to eliminate all of these terms. So
Maybe in the end, it's just a redesign of the
So, in fact, let me write this Lagrangian. Hopefully everything will be, things should be a little bit clearer with reference to that. Sorry, for all of the generators. Yeah, so I'm assuming a trace, like some Kronecker-Delft trace over, over the adjoint indices. So yes. Again, so you can try something different, and that'll be subject to the sort of more general results. Taking a subgroup of, find a subgroup H of G to the N where H is a subgroup of G. Okay. So regarding that last question, okay, in this Lagrangian, right, you're breaking some diagonal subgroup. And yes, you can rescale some of these fields if you like, but of course you will sort of upset the definition of the cubic and quartic terms. There will the actual subgroup, the gauge group, which is preserved by this, will still be a diagonal subgroup, even if you rescale these fields. And this is you can think of it if you like. The cubic and quartic terms keep track of this. Okay, so another way around what might be perceived as a no-go theorem is to write down a Lagrangian like this. So you're breaking some diagonal subgroup. However, you sort of include some explicit hierarchy in the gauge couplings, and also an explicit hierarchy in the VEVs. Now, to get to the zero-mode Lagrangian, you make this substitution, now without Q's. And you'll get a sort of a Yang-Mills theory out, also with a small gauge coupling. Now you'll see that this sum is essentially dominated by the smallest term in it parametrically. So the gauge coupling you get out is parametrically the smallest one that you put in this sort of geometric sequence of gauge couplings. And you might say, well, that's not that great. However, this thing still ends up with a very small gauge coupling, and the heavier modes, the clockwork gears or whatever, will end up with effective couplings to sort of charged particles, of which are much bigger, which are of order sort of other things on the lattice. So you can still couple things to the end of this lattice and get the effect where this zero mode couples with a lot lower strength relative to the other gears. Okay. Again, this so a graviton example of this, where you sort of have a hierarchy of Planck scales, you can see in Giudice and McCullough. All right, so that's about time, right? We should wrap up. I haven't touched on the extra dimensional stuff. I guess I should say very briefly that if you want something which deconstructs to a model like this, okay, assume this is abelian for now, with this sort of mass matrix which is somehow directional with the Q's, you'll want a bulk field in extra dimension with some means of localizing it. So sort of bulk and brane masses, okay, in this extra dimensional theory, and that affects this sort of symmetry localization which we saw in the abelian models. Again, if you're generalizing clockwork to things like this, again, see this paper, you can just have a massless bulk field, but with a warped metric. So specifically, a linear dilaton background will deconstruct to give you something like this. And you can see this is already very suggestive. You get factors of the metric arc here, which exponential factors, which give you, when discretized, this sort of hierarchy of QIs, and you also get exponential factors in front of what is effectively terms like that, where y is your extra spatial coordinate. Again, these have exponential metric factors out here, which give you something like that.
Is this in the original paper or in the response?
This model is in both. This model is in both. Well, specifically as applied to gravitons, which is directly analogous.
The point of the response then? What's the point of the response?
Well, okay. So, I don't know. No, it's.
I just want to know the differences, that's all.
No. So, well, I don't want to. I mean, there's a risk that I would misinterpret what they mean in a response. However, they say that you can. Well, for instance, to get between these two field theories which are written on the board, you can just do this field redefinition. So if you do a sort of site-dependent field redefinition, if you rescale all of these AIs by different factors of QI, you can get from here to here, modulo the sort of the cubic and quartic interactions, et cetera, which will actually keep track of whether you sort of have a hierarchy of, these are my words now, whether you have a hierarchy of sort of Planck scales or equivalently gauge couplings in the theory. So yeah, the two are of course very, very similar. You get the same mass spectrum. You get the same Clockwork mass spectrum for all of these modes. So a zero mode and the same masses for both, as you can see by making this field redefinition. But we would say if you include interactions such as the cubic and quartic things, or indeed interactions to other test particles, then you can distinguish.
I have a question. You mentioned that the extra-dimensional version of this has bulk and grain masses, but they have to be tuned, right?
Correct. To get a zero mode, yes.
So the question is, but you do, I think in your paper you claim that it's still technically natural.
Yes.
So I wanted to ask about that because so of course if you just put this in, right, then you get a free theory and you get a zero mode. So obviously it doesn't have any corrections, and that's fine. But if you add any other thing, and specifically in a 5D theory, you have to add all possible operators, right? Because your gauge couplings have dimensions, right? So then, why would that theory also preserve this shift symmetry?
By my understanding, that's not the definition of technically natural. The only requirement for technically natural is if you accomplish this tuning, then you get some larger symmetry, which is.
That's true, but the question is it possible to accomplish this tuning if you write down the full theory and not just the bulk and the grain mass?
Okay, so sort of higher order operators with more fields, more derivatives, etc.
It looks like it doesn't look like exactly like the supersymmetric version, right?
So it's true that it has been shown, at least for scalars with bulk and brain masses, you can enforce this tuning with some kind of supersymmetry. I believe that's true. I don't know whether it's ever been applied to the vector case.
Sure, but then why would that be?
No, I mean it is a tuning, but I believe by the accepted definition of technically natural is technically natural. If you make this tuning, you get this sort of view on symmetry group, I think.
Did we smoothly transition into the discussion part?
I know. Do I need to wrap up? Okay, in 2 sentences. Clockwork is a very neat model. We argue it's strictly a Abelian phenomenon, but if you sort of relax these various definitions or whatever, or construct theories like these, you can also go further. Full stop. Okay.